everybody, welcome to our channel Maths for All, and in particular to this particular series, which is a summary video series on calculus of variations. So let us connect it to the last video. In the last video, which is titled as Euler-Lagrange equation part 1, this video is Euler-Lagrange equation part 2. In the last video we saw that your functional is of this form, that is, you have one independent variable x and there is only one dependent variable and there is only first order derivative. Now in this particular video, what we are going to do is we are considering when your f, the integrand, is of the form one independent variable, two dependent variables, and you have here y dependent variable and z is a dependent variable and their first order derivatives. You can also go for function where you have more than two dependent variables. For example, here we have t as our independent variable, x, y, z, they are dependent variables, and then you have their first order derivatives. So you can keep on increasing the number of dependent variables. Right, here if you have only two dependent variables, then corresponding to each dependent variable you will write an Euler-Lagrange equation. For example, y is the dependent variable. This is the corresponding equation, Euler-Lagrange equation, which we have already studied in the last video. And z is the dependent variable. So this is the corresponding Euler-Lagrange equation which we had studied in the last video. So here we will have two simultaneously equations which we have to solve. So when you have two dependent variables, you will have two equations which you have to solve. And similarly, when you have three dependent variables, like here you have x, y, z, then you have three dependent like equations, simultaneous equations which you have to solve for each variable. For example, here t is your independent variable, x, y, z, they are the dependent variables. So for x also you will write one equation, for y you will write one equation, and for z you will write one equation, and so on. If you have n dependent variables, you can write n corresponding equations and you can solve it. Right. So I will start with the practice directly. We are not going to the proofs because that is the idea of the summary videos. Right. So let us look at the first question. Here is your question that show that this is a functional here, right, and these are the boundary conditions given to you, has an extremal value along this curve. So this is the parametric form of the curve. Now you look at this problem here. First you have to see x is not always the independent variable. Here the derivative is with respect to t, therefore independent variable here is t, independent variable is t. So you have one independent variable and dependent variable is x and y. You have two dependent variables. So you will write the Euler equation for each variable. So this is your function f. You can write it as 2x plus you can write it as x dash square plus you can write it as y dash square. Right. Now for the variable x, your equation will look like this. Curly f by curly x minus dy by dt. You have to note this. Here you have the independent variable, and in this case your independent variable is t. So you have curly f by curly x minus dy by dt of fx dash equal to 0, and here you have curly f by curly y minus dy by dt of fy dash is equal to 0. Right. So your f here is 2x plus x dash square plus y dash square. So you will get curly f by curly x is 2, curly f by curly y is 0, curly f by curly x dash is 2x dash, and curly f by curly y dash is 2y dash. Now you just put these here. So you will get 2 minus dy by dt of 2x dash is equal to 0. That gives you d2x by dt2 equal to 1. That gives you x is equal to t square by 2 plus c1t plus c2. And the second one, which is fy minus dy by dt of fy dash is equal to 0. That will give you 0 minus dy by dt of 2y dash is equal to 0. So you will get d2y by dt2 is equal to 0, which gives you y is equal to b1t plus b2. So this is your solution. Now because you are given the boundary conditions, so you can compute this constant c1, c2, b1 and b2. So let us see how we can solve these constants, solve for these constants. So you are given the condition that x of 0 is 0. So you can go back to your problem you can see that x of 0 is given to be 0, and y of 0 is 0, x of 1 is 1.5 and y of 1 is 1. So let us use that. So x of 0 is 0, that gives you just put 0 here, so you'll get C2 equal to 0. Y of 0 is 0, you put it here, you'll get B2 is equal to 0. Now x of 1 is 1.5, so you put 1 here, so you'll get this, and equal to 1.5, this gives you C1 is equal to 1. Similarly, y of 1 is 1, you put here y of 1, t1, so you'll get b1 plus b2 equal to 1, and b2 is 0, therefore b1 is 1. So you get the value of all the 4 arbitrary constants. So your answer is xt, you put the value, c1 is 1 and c2 is 0. So you get t square plus 2, t square by 2 plus t. And here you put b2 equal to 0 and b1 is equal to 1, so you get 1 t. Right, so this is what we wanted to prove, that your solution, your extremal lies along this curve, right? So hence proved. Let us look at one more problem. Here we are saying find the extremal of the functional this. So here you have a functional and you have to find the extremal. Here you see that you can see two variables y and z, right? And here on the left hand side you are given that y is a function of x and z is a function of x, right? So you don't confuse that there is only one dependent variable, because otherwise there is no y dash if you treat y as independent and z as dependent, right? So you have to make sure that you understand it properly, because y dash is there, it means that derivative of y with respect to the independent variable. So although you cannot see the independent variable here is no x, but here you can see that there is some x. Even if this is missing, here they have written only y and z, you have to assume some independent variable is there, because then only this y dash will make sense. So you can treat that variable as x, right? Okay, so it means that your function here is having one independent variable, that is x, and two dependent variable y and z, right? And your function is 2yz minus 2y square plus y dash square minus z dash square. So your Euler equations, you will have two Euler's equation. Here you have fy minus dy by dx of fy dash equal to 0, and the other one is fz minus dy by dx of z dash equal to 0. Now if you go look for the first, fy is here 2z minus 4y from here, minus dy by dx of fy dash, that is 2y dash equal to 0. And the second one is fz is your, if you differentiate it with respect to z, you will get 2y minus dy by dx of fz dash, that is you have to differentiate it with respect to z dash, so you will get minus 2z dash equal to 0. So the first equation here gives you 2z minus 4y minus 2y double dash equal to 0, and the second equation gives you 2y plus 2z double dash equal to 0. So you get y is equal to minus z double dash and y double dash plus 2y is equal to z. So you have this simultaneous equations, right? Both y and z are involved, so you have to solve it, right? And that is because this is not hard, you can just put the value of y is equal to z double dash from 2 into 1, so you'll get minus z fourth derivative of z plus 2 into minus z dash minus z equal to 0. So you can take negative on the other side, you will get d4 plus d 2d square plus 1d is operating on z is equal to 0. So you can write this as d square plus 1 whole square. So your roots will be, your d will be plus minus iota plus minus iota. This is from the auxiliary equation. So your solution looks like c1 plus c2x into cos x, right? This is how we solve differential equations with constant coefficients. So if you don't understand, then please look for differential equations, ordinary differential equations with constant coefficients. So how to solve ordinary differential equation with constant coefficients, there you will see this, right? And this is c3 plus c4 x into sin x. This is actually because you have roots here iota and minus iota and minus iota, so repeated roots, that is why this term is there. Right, now y is equal to z double dash with a negative sign, so you need to compute the double derivative of this. So you just compute the double derivative of this, you will see, you will use the product rule here. So you have c1 plus c2x into minus sin x, plus here you differentiate it with respect to x, that is c2 into cos x as such. Similarly here you differentiate it with respect to x, you keep it as such and differentiate it with respect to x, that is cos x. Then you differentiate with respect to x, that is c4 into sin x as such. Now you combine the sin x terms, right? So that is what you will get, and you combine the cos x terms also, you'll get this. Right, now here minus c1 plus c4, I am calling it another constant a, and minus c2 I am calling it as another constant b into sin x, plus c2 plus c3 I am calling it as another constant c, plus c4 I am calling it as g in x cos x. So similarly we saw that if z is c1 plus c2x, c1 plus c2x cos x plus c3 plus c4x sin x, if we differentiate it once we get the same terms, just the constants are changed, right? So if you differentiate it once more, you will get same thing, just the constants are changed. So this is your, with a negative sign, this is your y, right? So you wanted to find out y as well as x, so you get this is y and this is your z here, right? So this is how you solve these problems. Let us look at one more last problem here. So here we are saying find the extremals of the functional. You are given a functional, you are asked to find the extremal. Here you see that, you can clearly see, very clearly you can see that your t is independent variable, t is your independent variable, and your x and y, they are dependent variables. So you have to see this thing, and these are the boundary conditions given to you right now. So you will write two Euler's equations, so corresponding to the variable x. So this is your f. Here I can write it as this, x dash square and y dash square, right? Now the Euler equation corresponding to the variable x, that is fx minus dy by dt of fx dash is equal to 0. So you'll get 2y minus dy by dt of 2x dash equal to 0. That gives you y is equal to x double dash. And here fy minus dy by dt of fy dash equal to 0. So you get 2x minus dy by dt of 2y dash equal to 0. That gives you x is equal to y double dash. Now you have these two equations and you have to solve it. You just put value of y from here to here, you will get x fourth derivative minus x is equal to 0. So d4 minus 1 x is equal to 0. So that is d square minus 1 d square plus 1 operating on x is equal to 0. So you get d is equal to plus minus 1x and plus minus iota x. So corresponding to plus minus 1x you have c1 e raised power t. So you note that t is your independent variable, plus c2 e raised power minus t, plus c3 sin t, plus c4 cos t. Now you see that your y is x double dash. So you want to find out the double derivative of this particular quantity here. So the first derivative will give you, if you differentiate it once, you'll get c1 e raised power t minus c2 e raised power minus t plus c3 cos t minus c4 sin t. Differentiate it again, so you'll get c1 e raised power t plus c2 e raised power minus t minus c3 sin t minus c4 cos t. So you get x double dash also, this is equal to y. So this is your y here, right? So ultimately you get that this is your y and this is your x, right? Now you are given the boundary conditions, you can use those to find out c1, c2, c3, c4. So for x of 0 is given to be 0, that will give you c1 plus c2 plus c4 equal to 0. X of pi by 2 is equal to minus 1, that will give you this equation. Y of 0 is 0, that will give you this equation. And y of pi by 2 is 1, that will give you this equation. And you can solve all these equations, that will give you c1 equal to c2 is equal to c4 equal to 0 and c3 is equal to minus 1. So your x will look like, because you get c3 is equal to minus 1, so your x will be minus sin t and y will be sin t. So your solution here is x is equal to minus sin t and y is sin t, right? So you see here, this is how you solve for the Euler-Lagrange equation when you have two or more than two dependent variables. In that case you will get a system of equations which you have to solve. So you should you can see that you need to know the concept of differential equations, because Euler-Lagrange equation is a differential equation. You have to solve the differential equation, so you should know how to solve differential equations, right? Okay, thank you for watching this video, and I would also like you to please share this video and please subscribe to our channel if you have not. And also in the comment section you can let us know if you have any problems or doubts in calculus of variations. We can actually, we are going to make a series of questions on the calculus of variations, and we may include your problem as one of our question, right? So you can write in the comment section if you want any of your problem on calculus of variations to be considered, whatever we are teaching to be considered in our next video, which will be on the practice problems on calculus of variations. Thank you so much. Stay connected and happy learning.